welcome to our presentation about, I should say, two-wire bus that has been used with the SMBus protocol for many, many years. And recently, EDSFF specification and other standard organizations are defining how to improve it, upgrade it to I3C. Before I go into merits, there will be, let me introduce the presenters. Myself, Janusz Jurski, I'm representing Intel. There will be, I hope he's coming in a moment, Myron representing Solidigm. We have Anthony and Juan from Intel. Unfortunately, we're missing Brian Kelly and Zbigniew Hukwiński. Microsoft and Intel, they had conflicts, they couldn't come. But special thanks to them, because this presentation and in fact this whole work wouldn't really happen without their help. Special thanks to them. The plan for our presentation is such that we'll talk about what's really wrong with SMBus architecture, what are the limitations. Then we'll talk about the solution that is based on I3C, the one that EDSFF defined. Then we'll show some experimental results with a system that we built that implements the EDSFF flow, and hopefully we'll save a few minutes for questions and answers. Myron has just arrived, so coming back, that's one of the co-presenters from Solidigm. Let me move to that first part. So this is about just kind of a background. SMBus has been defined about 3 decades ago, a long time ago, and in fact it has been an upgrade of I2C protocol that's 4 decades old. So it's a very old protocol. It has been very successfully used across, I think, all the form factors that I'm aware of. For manageability purposes, and the success is perhaps because it was a very simple, robust enough protocol, just over simply 2 wires, 2-wire bus, and that's how it has been designed. One of the well, it wasn't ideal. There were some issues with SMBus, and I wanted to focus on 2 of them. One is related to the addressing architecture. So the SMBus specification didn't really require SMBus devices to support dynamic addressing. So if you connect multiple devices to those common 2 wires, you end up with address conflicts. And one of the common typical solutions that has been adopted broadly in the industry is to use a multiplexer on the bus, that the bus is no longer continuous. Instead, the multiplexer allows to interrupt the connectivity and only connect to the device that the BMC wants to talk. So instead of 2 wires connecting the BMC to all the endpoints, the BMC can only connect to one of the endpoints, that it chooses to. There has been attempts to fix it a little bit, like for example, the CAM specification defined a requirement that devices should support ARP, dynamic addressing, but unfortunately, the base specification that required vendors very often don't implement it even until today. So that's the reason why typically, or in majority of systems, multiplexers are in place today. They also have another advantage from security perspective. They prevent one of the endpoints to talk to another endpoint directly, because the pure SMBus specification allows that, enables it with its arbitration protocols, and that's undesired. So this solution worked very well for all the legacy use cases, basically all of them are characterized by the fact that they are initiated by the BMC. The BMC either performs a simple read, through read or something like that, or some write to EEPROM or something similar. All of that controlled by the BMC. But these use cases have changed over time, and a good example is the MCTP protocol that has been defined perhaps about a decade ago, a little more. That is on, when it runs on top of SMBus, it relies on the original arbitration mechanisms and all the ACKs, NACKs that SMBus uses. And unfortunately, this assumption is not compatible really with the MACs that are in the system on this bus, because the bus is no longer continuous, so devices cannot really see themselves, the other device directly. So I have an example here, a simple flow where the BMC sends a request to the endpoint, MCTP request. It immediately gets an acknowledgement because it's the same transaction, but then the device, the endpoints, needs to prepare the response. And preparing the response, sometimes it may take a while, especially if this involves some crypto operations and things like that, which are the new use cases, I would say. And during that time, the BMC has to either wait a long time, or perhaps after some timeout, it may switch away and go and check what's up with the other endpoints. For example, check the temperature every so often. So if the endpoint attempts to respond according to the MCTP protocol, this is how it's defined in the specifications, then it will try to transmit to target the BMC, but there is no way to talk to the BMC directly because the MAX is switched to another device. And the packet is not acknowledged. The endpoint will notice that. It will attempt to retry, but again, the retries often fail and the packets are lost. That's how they will show in a moment real-world experimentation that basically confirm this scenario. That's not the only problem. Maybe even a bigger problem is the fact that the MAX switching happens really asynchronously without coordination, and for that reason, the ongoing transactions can sometimes be truncated. And in a small scale, it is addressed by checksums and other mechanisms that verify the correctness of the received data. But when you think about data center with hundreds of thousands of systems, multiple transactions per second, multiple buses and so on, then those mechanisms like checksums that have been defined with sporadic errors happening from time to time only, then they sometimes may allow truncated packet to be consumed by the device and leading to unpredictable behavior. That's unacceptable. Another issue because of the MAX switching is the fact that such glitches that happen on the bus, they sometimes confuse the device and they hang. So that's another problem. But maybe focusing on this scenario where we have a kind of long-running task, or sometimes basically the endpoint trying to send asynchronous communication to the BMC, some alert or some other notification. I have a trace here showing basically this scenario. So the top picture shows a successful transmission of the request from the BMC. Then there is some time when the device prepares the response and a successful response received by the BMC. But in this picture, we are showing a scenario when the MAX has been switched away, and the endpoint, when it tries to send the response back, it will not get an acknowledgement. It will retry, and in the zoomed in trace, we can see that the retries happen very frequently. They actually happen every 4.6 microseconds. That's exactly how the specs define it and how usually that's hardware, how it implements it. So there is really no easy way to fix it. There are some workarounds to work with these behaviors. So first of all, very often BMCs just wait for the response, and sometimes it's a reasonable approach because they can wait for 10 milliseconds or so. But sometimes it's a long period of time, hundreds of milliseconds or so. That's unacceptable. That's very inefficient. Bus is mostly idle for the whole time. There are some protocols such as NVMe-MI that are upper layer protocols, but they attempt to fix the problems with lower layer SMBus. It's kind of upside down that what we would want. And to some extent, they succeed with, defining the workarounds. It's worth to mention that retries don't really help because you will just hit the same scenario again and again. And I think the biggest problem is that every device behaves differently. The time to respond is different, and there are too many different behaviors that you have to accommodate in your BMC code. That's terrible. And actually, all these workarounds, they don't really work for truly asynchronous communication. When there's an alert or a similar scenario when the BMC cannot predict when to wait for the response, then they don't work because their transmission period is just like a millisecond or two. So the BMC will miss it. So with all this in mind and the workaround attempts, the EDSFF specification defined the solution that is based on I3C, and this part I wanted to give the stage to Myron. He will describe the solution architecture.
Hey, thanks JJ for showing the problem. I get to write in and give you guys a solution. Well, it's what we think the best solution is right now. So I3C efforts started 10 years ago. In 2016, they published the first MIPI I3C 1.0 spec. 2 years later, they published a basic version of that spec, and that's what kind of we're rallying around here. The I3C solution is much bigger than what MIPI produced. MIPI produced something like I2C. Then you have to wrap that with how MCTP traffic is going to flow over on top of that. Then we have to come up with the new hub architecture, like stuff that goes on the platform from the guys at Intel. They've already put this into a reference design, and you can get that from them. And then all these other companies have to build the silicon to make this all work. So there's some part numbers there for the hubs. Partial part numbers, because there's some options on those where the X's go. The off-the-shelf components are from everybody. So like the people who make the BMC, Novatron and ASpeed, yeah, they both have I3C built into their hardware already. There's microcontrollers that if you want to put emulation of serial EEPROM or something onto your device, that exists already. There's a bunch of other sensors. So a bunch of companies, TI, ST, Microchip, they all make I3C components ready today. So this picture is showing you how big the ecosystem has rallied around the I3C standard, and that all the hardware you need is available today. You're still going to probably make something better yet, but there is enough hardware today to make a solution. There's some links there, the I3C links, if you want to follow those to get more details. The SNIA link is a second line there. That one shows how we negotiate from SMBus to I3C, and you use the same exact two wires, and one of the main differences is the voltage. And looking forward, we wanted to go to lower voltages. Already TSMC doesn't let us go to 3.3 volt tolerant anymore. So the I3C spec, we wanted to go low enough that we could work with silicon, but not so low that we lost all our noise margin for like long traces across the backplane of the computer chassis. So right now we've got at 1.8 volts, which is very nice because that also aligns with M.2, and they're all at the same voltage now. It starts off at the old compatible voltage, and it steps down when it realizes that it's in I3C, but we'll get to that in a second. So one of the problems that JJ talked about, or maybe he didn't really talk about this one, in SMBus, everything has a fixed address. and you can't change the address on most stuff. Some of the microcontrollers have ARP, but all the serial EPROMs, they're fixed, their address is set. What that means is that if you're building a platform, say you're a Dell, Lenovo, HP, that kind of a company, that you now have to track every single address that cards that plug into your compatible system are going to use, so that you don't have conflicts where you got two devices with the same address that are going to be on the bus at the same time. So what SMBus did for that is they did ARP. ARP never really caught on with PCIe. It was in there, but you could have used it, but it didn't really catch on. For I3C, it's in the physical layer right from the very beginning. So everybody will have the common way of assigning addresses and making sure that we don't have to keep those libraries, that everything will just get defined as it enumerates. Let's see what else is here. The MUX technology is so say that you had the previous example where JJ was talking about where you have a switch that switches to different ports. And you can, I want to talk to this port, finish talking to them, I'm going to talk to the next port. That can go away with the MUX, the new MUX that's defined for I3C, and we'll get into, there's a whole slide coming on that. And security is improved by the clock being generated only by the controller. All the devices are listening only in I3C mode. They cannot touch the clock. So one of the problems we had in SMBus is that someone could go jam the clock. With clock stretching, you could end up clock stretching and not letting go. You could clock stretch longer than it wanted you to clock stretch. There's all kinds of gotchas around that. But in I3C, that all goes away. The clock is only generated by the master, which is now called the controller. And the devices, which used to be the slaves, are just going to be driving the data as synchronized to the master's clock. So that's some security there, but that's also security in another way, that you can't have one peer initiating conversations with another peer. It all has to go back through the top, through the controller that owns the whole network. So to do traffic, if you want to initiate traffic from the device, there's two ways that we have defined that. One is you can use an IBI to say, hey, I have an interrupt. I want to send some traffic. That's the IBI, in-band interrupt. And if that triggers, what happens is you set your data line low. It looks just like a start condition in SMBus. When the controller sees that happen, they'll start sending out the clock, and the device just sends out the data to follow that clock pattern. The other way that we can do it is we can do polling just like we did in SMBus, where the controller just checks to see if each device has some traffic. One of the nice things you'll see when you use the hub is that you no longer have to switch from channel to channel. You could send out a poll to all the devices to have them respond if they have traffic. And just some higher speeds, that you're obviously aware that I3C comes with some really good speed improvements, both latency improvements and bandwidth improvements. And an in-band reset. So this is another neat thing. So in SMBus, you typically had a separate wire for doing reset. You could use the S-clock low for 25 milliseconds to 35 to trigger it, but a lot of companies didn't implement that. So this one, from the beginning, it has a standard reset recovery mechanism. And if you got questions, just jump up, raise your hand, whatever, get my attention, I'll divert to that. So to make this work in the computer ecosystem, we had to take what MIPI developed for I3C, and then we had to wrap all of the communications protocols similar to what we did with SMBus. So MCTP did that with the I3C binding, and you can go get the full details right there. So some things that MCTP adds on top of what MIPI already had defined is the checksums, and to make the communications robust. And where's that on here? So we talked a little bit about the single I3C controller from a security perspective and controlling the clock. The next thing down was the IBIs, and what we're saying there is that the IBIs, where the device wants to talk to the host, it can choose to do the IBI method if it's been enabled. So the controller still has to say, yes, I want you to use IBIs, or the controller can decide, I just want to do polling. And so that's why they're optional. If you don't respond to an IBI, the communications are not lost. So the controller has some flexibility there. It can ignore IBIs if it doesn't have time. It can go back and fetch that content later. It's not dropped. And then there's I3C has, that's a big difference from SMBus, where SMBus has some defined data patterns, like where you send a start and a start address, and then you have your maybe your block length and just a bunch of data and your checksum at the end. I3C goes one step further, and it says, here are some common command codes, which are CCCs. We expect all devices to support. And then there's some optional ones as well. Some of those command codes are used for things like assigning the dynamic address. The other ones are used for discovery, which protocols are supported, and for MTU negotiations, so you can set the size of your data packets, and for enabling, disabling the IBIs. Then, I guess the binding improvements over so you might say that, well, I3C has some issues, right? So what we did is we went through all of the different ways that we thought I3C could get hung. And we checked that there was a robust recovery mechanism and detection mechanism that they were hung. So that's what's referred to here at the bottom. That's all built into the MIPI binding spec, and you can get the details there. But it's stuff like a CRC, that's like we had for SMBus as well. And where was a different one you want? Yeah. Okay.
Hey, Mark, if I were to what you just said.
Oh, you said it. Oh, did you want to say it? Yeah.
Whole section of robustness and recovery improvements that is defined in MCTP binding that applies to I3C. That I3C original pure I3C didn't really have. So this includes some retransmissions, how to deal with lost transactions, or like, for example, this checksum mechanism.
Yes.
I take it these bindings, this binding is transparent to anything that happens on the data model about PLDM, NVMe-MI, SPDM, etc.
Yeah, well, this is be like the middle layer, right? Like you got your physical I3C at the bottom. Oh, sorry. So the question is, how does this relate like to PLDM and to other higher protocols? And so the bottom would be your physical, that's MIPI defines the I3C. Then there's this transport mechanism defined by DMTF. And then there'll still be these other protocols on top, PLDM, NVMe-MI, SPDM, and those ones are almost ambivalent to what's underneath. Maybe there's a little bit of interaction with what's underneath. Like NVMe-MI, for example, has some physical hooks where it can change the speed and stuff like that. But really the PLDM should work regardless of which transport mechanisms you have underneath. That answer the question?
Yeah.
Okay. And then so now bringing it back all to SNIA, what SNIA did is it took what was being developed in those other specs, and it says, how do we put this onto the EDSFF connector? And we were there's this race condition, right? Does PCI SIG define this? Does SNIA define this? Who's going to write this down? And nobody was doing it, so SNIA took the initiative and created this flowchart. We're not going to go into the iChart here to tell you what's on the flowchart. But SNIA created this mechanism whereby you could be backwards compatible with SMBus. So the wire basically starts off in SMBus mode, and then it sends a 7E as a special address that wasn't allowed in SMBus. When you send that one to a I3C device, it will switch off its SMBus transmitter. And then you can check again to see if there's any SMBus-only devices on the network. Then you'll send another 7E, which will switch the voltage, which we talked about earlier, down to 1.8 volts instead of being at the 3.3. And then after that's successful, you can go into I3C communications and assign a dynamic address. And you can get all that detail just by going into the SNIA, the TA-1009 spec. Anything I missed here? And so this is, yeah, go ahead.
How's your compatibility with control hardware?
So you mean this off-the-shelf hardware we just talked about?
What was the question?
Oh, the question was, how is this compatible with hardware? And I'm not sure which specific hardware you meant.
You have two implementations currently, right? The NVMe speed.
From the BMC perspective, yeah. So what the BMC in that case would do is it would probably have an I3C port and an SMBus port separate.
So it's
Because,
bouncing onto those two.
yeah, that's how you guys are doing it in your reference design at Intel?
We will show that later.
You'll show that, okay. From the device side, the controllers that we've used are all compatible with the SNIA flowchart. And you'll see there's going to be real live device scope traces and stuff like that that we've run. Go ahead, John.
So there's a little bit of an identity confusion. It's SFF, not SNIA.
Sorry, the SFF within SNIA,
Anthony will address that.
he'll fix that up. Okay. Yeah, so it's the SFF 1009 spec. All right, then I think that we'll hand this off to the hub discussion from.
Okay, hi everybody. I think addressing part of that question, right, on hardware compatibility. So Renesas and Intel partnership on the definition of a key component that addresses this SMBus issue, compatibility across SMBus devices and I3C controllers, as well addresses the issue for trying to implement the I3C protocol in a server storage type of environment, because as you may know, I3C was defined for mobile type of applications, right? So this I3C hub, or also known as I3C intelligent switch, the high-level definition, you can see this on this picture, right? So primarily it has two controller ports that you can use to connect to upstream I3C controllers, and then you can have up to 8 target ports that can be used to connect downstream I3C or SMBus devices. So how this device solve all those problems, right? For example, let's start with the arbitration and address issues of SMBus, right? In each of the target ports, we have a dedicated SMBus agent. That SMBus agent is basically consists of an SMBus compatible controller and an SMBus target controller, right? They are fully compatible with the SMBus specs, your voltages, clock stretching, which are not part of the I3C spec, right, or not compatible to I3C. The communication to the upstream controller is done in a non-transparent bridging, right? The way it works is the SMBus agent, for triggering transactions, the I3C controller will access the hub resources via a dedicated target device, and the target device provides access to the hub status, controller registers, and all the data buffers that are going to be used to send or receive packets, right? So for issuing a transaction from the I3C controller point of view, the I3C controller will provide the SMBus transaction frame and the data payload, and will request the SMBus controller to issue that transaction, right? The SMBus controller will handle and manage all the low-level SMBus protocol. For receiving transactions from downstream devices, the SMBus target agent is concurrently connected to the target port, so they can receive transactions at any time asynchronous, right? Without having the I3C controller being connected, right, to that specific target port at all the time, right? The SMBus agent manages that asynchronous communication that was not possible to do with I2C type of MUXes, right? So when a device starts a transaction back to the upstream controller, that transaction is going to be consumed by the SMBus target. And at the end of the transaction, the SMBus agent will issue an invalid interrupt so the I3C upstream controller can service and consume that transaction. How do we deal with, hey, I mean, if we have back-to-back transactions? So SMBus agent, the target agent has 2 data buffers. Each data buffer can consume a full MCTP packet. So we can service at the I3C higher speed at the upstream, all those low-level SMBus transactions that are happening at the lower speeds. If those both buffers are filled and the I3C controller, for whatever reason, they didn't service those on time and empty the buffers, So we implemented a bus busy condition, right? The SMBus agent will pull the data line low to indicate the bus is busy and prevent the downstream devices to attempt to send another transaction. The device will have to wait for the bus to become idle in order to attempt another transaction, right? In this way, we prevent losing packets, right? We hold the downstream device until the upstream controller service those pending transactions, then the data buffers will be empty again. The SMBus agent will release the data line high, and the bus will go into idle condition, allowing subsequent packets to be sent from downstream devices. Because each target port works independent of each other, right? We have SMBus agents dedicated to target ports. Then we can have SMBus devices with the same address. We don't have address contention problems because each SMBus target port is truly logical and electrically isolated, right? So we can have the same target device address, and we don't have address contention issues. They are truly asynchronous, so they can receive or send transactions at any time without depending for the I3C controller allocating any time to particular bus segments, so they can run asynchronous to the I3C upstream controller. The other benefit and solving the problem of mixing legacy SMBus devices and I3C devices is each of the target ports can work independent of each other. You can have I3C capable devices on specific target ports. Those are connected to the upstream controller via an I3C network, and they will work transparently, right? There is a transparent communication from the controller to the target ports as if the hub was not there. So this is what we call is a same logical network, but the hub provides electrical isolation, right? Each of the target ports and the controller ports are truly electrically isolated, so we can support higher bus capacitance, right? I mean, we have tested up to 250, 350 picofarads compared to the I3C spec, which only supports up to 50 picofarads loading. And lastly, we can use the hub as a port expansion, right? I mean, a single I3C controller can have an expansion of 8 SMBus or I3C ports to connect to downstream devices. Okay, so all this looks great in paper, right? I mean, but we didn't stop with just PowerPoint engineering. What we did was actually doing a proof of concept, right, in partnership with Intel, Renesas, Microchip, Solidim, and put together this system, right? The pieces that we have together here is we have an Intel I3C ready motherboard with Intel I3C ready backplanes. On the motherboard, we have the I3C hubs that connect to downstream devices, either to PCIe, CAM, adding CAN form factors, and another hub is the one that has the expansion connected to the different backplanes. In this typical application we have on some of our storage servers, we can support up to 3 backplanes. Each of the backplanes has an I3C hub, and downstream the hub, we have connected this NVMe in an EDSFF E3 form factor with SMBus, an I3C capable device from Solidigem. The physical topology that you can see down there is quite challenging. I mean, we're talking about 13 inches of PCB trays on the motherboard, plus 60 inches of cable routing, plus 5 inches on each drive backplane. So a pure I3C topology will simply not work in this type of application, right? That's why we have different hubs to provide electrical isolation and to maintain the logical functionality of a single I3C network. First, looking at the electrical level, right? How capable are we of running this I3C improved bit rate, right? With the theoretical of 12.5 megahertz, in this kind of challenging topology, we were able actually to run at the 10 megahertz bit rate. We took a snapshot of the clock signal on each of the backplanes at the I3C clock at the hub input, and we can see that the signal quality is relatively okay, right? We were able to run at 1.8 volt I/O voltage, 100 kilohertz open drain frequency, because it has the same limitation as an SMBus open drain type of buffer, but when switching to the push-pull frequency of the I3C frame, then in this harsh environment, we were able to run at 10 megahertz operation. Question?
22.
22, you asked if we can reach 22 megahertz?
Did you try?
No, we didn't try. we actually tried 12.5. I mean, we tweaked the duty cycle, and we were able to operate 12.5. But yeah, I mean, beyond that, as we start seeing now signal integrity problems.
But to John's question, that's double data
double
rate,
data rate.
and so it doesn't actually change the frequency response. So yes, if you had double data rate capable hardware, it should be able to go to 25 if you do the tweaking, or 20 if you just do it without tweaking.
Yeah, actually, the double data rate brings other benefits, right? Because it changes the clocking mode, so it makes it easier to reach to the 25 double data rate. But on this hardware concept, yeah, the hub specifically is only capable of single data rate at this point. Okay. Well, this is just the typical system architecture that we expect for PCIe, CXL, NVMe devices, right? You have your motherboard with a I3C capable BMC controller, having the I3C hub to connect to downstream devices, and those downstream devices, it could be I3C capable or SMBus legacy devices. So now going from to the logical part of the testing, right, to the functional testing. Here are some of the snapshots of the flow that you overview and give a quick high-level overview of the flow. Here are the actual experimentation and traces that showcase that flow. Basically, for example, here is how do we detect I3C capable devices, right? In the flow is basically, hey, we send the first this CCC, right, common command code, so that the typical I3C CCCs will not be acknowledged by legacy SMBus devices, right? So we send the CCC. If we receive an acknowledge, then we know there is at least one I3C capable device. Then we go through an SMBus discovery process, and this discovery process is just basically pinging every single possible SMBus address, so to guarantee there is no SMBus device if we didn't receive any acknowledge. Once we know there is no SMBus devices and at least there is an I3C capable device, then we send another CCC in order to switch or indicate the downstream device to change from the legacy SMBus to the I3C mode. And finally, we change the voltage, right? I mean, we go from the 3.3 volt, which is SMBus voltage, to the lower 1.8 volt of an I3C transaction. In this other experimentation, right, the trace is showing an actual MCTP trace request in an I3C mode with interrupt. So this is the whole trace for the MCTP request done by the controller to the down device. And here is the IBI or interrupt request from the device, and then the response and service from the controller to that interrupt from the device. And finally, you can also disable IBIs as JJ mentioned, right? I mean, you disable the IBIs and then you can change into a pooling mode, right? You can just send get the status CCC. So the get the status CCC will get the request and you get the status from the device and you will get the response from the device to this get the status CCC. Okay, and Anthony will just summarize for JJ. Good job.
Yeah. So just to summarize and open for questions, the I3C architecture that we presented, and it has been adopted by EDSFF, it addresses the key issues that we had with SMBus, and it addresses them in such a way that the legacy devices, SMBus devices, don't have to change. It's only the platform that is impacted, so the BMC or instead of the MUX, the intelligent hub can be used. And it works in such a way that the legacy devices will operate better than with the typical SMBus architecture implemented today. That's because all these protocols have been designed with all these use cases in mind since the very beginning. It's the BMC that initiates all the transactions and so on and so on. Now, this has already been adopted by EDSFF, but there is work in progress, and we encourage everybody to take part in this, to adopt it broadly in other specifications, help with that. So, for example, there are some links to the specs that potentially could adopt the I3C upgrade of SMBus, especially because it's backward compatible. Especially the PCI SIG, there's work in progress. There is some review going on right now. So if you remember, please go open the draft, review this, provide feedback. That's what is, I think, important is we are hoping that this will be consistent solution across all the different specs, because SNIA decided to donate the flow that has been adopted by EDSFF to other standard organizations, and it has been already donated to PCI SIG. Just call to action: make your product plans with this new architecture. From Intel, we already have the reference platform hardware ready. The firmware, production quality firmware will be ready with PCIe 6.0, because this is when the PCI SIG is planning, hopefully, adopt the new flow. As we heard earlier from Jeremy, he upstreamed already some of the code. One of the previous presentations, he already upstreamed some of the code that can also be used broadly. Of course, we are still working, planning to upstream or are interested in upstreaming the other code that we have, for example, related to the I3C HUB. We're looking for other partners to co-validate this solution, especially there's a request from Solidigm. In addition to Intel, they would want to work with others. So with that, I think we have still 5 minutes for any questions. Yep.
Can you comment on the licensing requirements for HDR and how it can implement open systems?
Repeat the question.
The question was about licensing requirements for HDR, and the HDR is the high data rate mode for I3C, defined by MIPI. And what was the other part of the question?
How we can implement an open system.
Mm-hmm. Yeah.
At this point, we're only planning on supporting I3C basic, so there will not be, we will not be looking at some of those advanced modes that are supported by the mainline I3C spec.
That's me just fine, thank you.
Yeah.
Well, in fact, there are some changes coming, because actually they have been already published by MIPI with the 1.1.1 version of the spec. So updated specification actually changes some of the licensing requirements and opens the higher speeds, not all of them, but some of the higher speeds broadly for adoption by anybody. This opens the door for extensions to higher speeds.
Yeah, and that's more of looking towards the future, right? I mean, the original reason why we went to I3C basic was we wanted this more open. We wanted to be able to propagate it and not have to deal with those licensing concerns.
Yeah, we can't write drivers against that.
Exactly.
Yeah,
Exactly.
So please check the latest version of I3C Basic 1.1.1. This opens the licensing more broadly.
Go ahead, John.
I will put this as a question. Who owns the licensing rights for I3C non-basic?
Okay, so John's question is, who owns the licensing rights for I3C main? And John, do you want to answer that question?
Good, you've got the mic.
I can repeat.
MIPI.
Yes. So keep it.
Openness will depend on MIPI's desire to be open.
Yeah. So John's comment is MIPI ultimately owns I3C, so it's up to their openness for being able to provide that spec out to the world. Now they were They were good. They were gracious enough to provide out I3C Basic, which has helped a lot of people. I mean, there's a lot of there's other organizations that are using I3C for non-PCIe applications. So.
So all this what we presented, this relies only on I3C Basic, and there's no interaction with all the restricted content here. This applies to all the specs like MCTP binding spec. It only relies on I3C Basic. There's no dependency on any licensed components of the I3C specification.
Yeah, and I mean, this has been part of the 10-year journey that JJ, I think, mentioned at the beginning, right? This would have been, you know, you have to work through a lot of issues to get this from, you know, from concept to spec to actual application. So this has been a long and grueling journey, but it feels like we've at least at the finish line to start implementing these things. So.
Yeah, another question, John.
One more question, maybe just one. In signal integrity, the fun experimentation which was done, did you see what it looked like at 1 volt?
Okay, so John's question is essentially, can we run at a lower voltage than 1.8 volt? Like if we were to run at 1 volt, which is allowed per the MIPI I3C basic specification. Because MIPI can run at several different levels. We chose 1.8 voltage as a starting point. So, Juan?
Did JEDEC choose 1 volt?
We have that debate of aligning to 1 volt JEDEC or why not deviating to 1.8 if we have good reasons, right? We did experiment at 1 volt, and at 1 volt, the signal characteristic, the channel doesn't change, right? It's just the drivers, the level, they scale accordingly between 1 and 1.8 volt, right? The reason we recommended 1.8 volt because it gives you more margin for external disturbances, right? That is basically noise and crosstalk, right? So we choose 1.8 volt to get more margin for these harder topologies which are going to be subject to crosstalk and so on. That's the reason we choose 1.8. But 1.1 will work as well, but with less margins.
I guess one other statement there. Keep in mind the DIMM topology is very different than the SSD or other devices on a backplane topology. So lot longer of a run to get crosstalk. We just got the signal that we need to wrap up. So if there's any other questions, you know, please feel free to talk to one of our presenters after this. Thank you, everyone.
Great. Thank you.